So, dear friends, here we are. I'm going to allow Henrique to control the slides according to his judgment. I am going to talk for 2 minutes at most by saying, what a mouthful of a title. But geometrodynamics means something like the geometry of space changing over time. And that is one way to think about general relativity or kindred theories. Functionalism is a philosophy doctrine. And this paper is urging that geometrodynamics gives you a lovely sharp illustration of the philosophy doctrine functionalism about time, meaning by that the temporal metric, the clock, the readings of a clock. And the first slide gave a philosophy background reference to the Pittsburgh archive that you could pursue if you wanted. But if you just search under the names, you get led to it. It's called Functionalism as a Species of Reduction. But in any case, this paper is going to urge, well, not just that geometrodynamics gives you functionalism about the temporal metric, but actually the general idea of geometrodynamics gives you 3 such sharp and vivid illustrations. So what is functionalism? Well, it's not Walter Gropius, and it's not Levi-Strauss. So forget architecture and forget anthropology. This is in-house, pure academic philosophy here. It's a buzzword from the 60s for the idea that many properties can be specified by not kind of scrutinizing their intrinsic nature, but by their pattern of relations to other properties. And the classic example is being locked. A door can be locked, a padlock can be locked, a combination lock or a key lock can be locked. Being locked isn't a matter of being made of metal or being made of rotating wheels. It's a matter of blockage of access being overcome by special knowledge or possessions, right? Notice how abstract that is, right? Access, blockage. So there's a web of relations, and the notion of being locked is multiply realized, as they say in the jargon, by a combination lock, a keyhole type lock, and so on. So our hero in this tale is David Lewis, who in 1966 and 1970, very early papers by him, stressed that functionalism can be combined with a Nagel-type reduction. So Lewis emphasized that this idea of specifying a property by its web of relations doesn't have to just be done for one property. It can be done for several or many all at once. That won't be a big thing for us because we're only interested in one property, the temporal metric. But the other thing he emphasized was that these definitions that specify, or specifications, can actually contribute to a Nagel-style reduction in which what Nagel and the tradition called bridge laws are not hypotheses or guesses, which was how Nagel and others mostly conceived them. They're actually deduced in a certain context, and we'll see an example. So those 2 features are downplayed later, but we wish to revive them. And without going into detail, there is an Australian movement, not known in the philosophy of science, but in philosophy of mind and metaphysics it's known. It's called the Canberra Plan. And they like Little Roman 1 and Little Roman 2. So our topic is space-time functionalism. And as the lock example shows, it's something like to be locked is to act like you are a lock. So space-time is as space-time does. Or, if it looks like a duck and walks like a duck, then it is a duck, right? So many ways that idea can be developed, but our concern is with the idea, a Machian or relationist or a Harvey Brown type of idea, that the physics of matter or matter and radiation, ponderable matter or electromagnetism, that contributes to determining space-time structure, chrono-geometry. Maybe it even determines it. Maybe it even explains it. And so we're going to give you 3 examples, not just of functionalism, but a functionalist reduction about this concept, the temporal metric. And at this point, there you are, listed there. There's a great paper of 1976 by Heumann, Kukash, and Teitelbaum. There is a program in the last 10 years with mostly German authors, led by Fred Schuller. And there is finally, if I may say so, dear Henrique is too modest to say this, but there's a wonderful paper of 2016. Now, all 3 of these enterprises, these projects that you see referenced there, are general relativistic in a sense. That doesn't mean they just accept, let's accept general relativity. I'll assume a Lorentzian manifold. I'll assume the Einstein field equations. No, it's much more, I'll assume a manifold, or I'll assume a manifold with some structure, and then I'll do some clever stuff and get out something good, which is also part of the general GR picture. So what happens in HKT, as we call them, is they assume that there is a manifold with a Lorentzian metric, but they then go on to give you beautiful information about the geometry of space. Quite striking information about how the geometry of space changes over time, starting with a Lorentzian manifold. Schuller, Duhl, Giesel assume a manifold and stuff about it, but they do not assume a metric. There's no metric. There's no Lorentzian metric. There's rather general conditions about matter fields with no mention of a metric. And in Gomes-Shyam, there isn't even a 4-dimensional manifold. In Gomes-Shyam, there's just a 3-manifold and postulates about it. But all 3 enterprises end up deducing a very famous version of GR, which is the evolution of geometry of space by a Hamiltonian first written down by Arnovit, Deser, and Misner, so-called ADM. This is all, in a way, a cousin of Barber and Bertotti, which some of you may know about. And at this stage, I'm shut up. Sorry, I went on longer than I hoped.
No, thank you, Jeremy. I don't know, can everyone see my screen and myself?
Yeah, good.
Okay, thank you so much for that, Jeremy. And I almost feel sorry that I have to now take over, because I could listen to you talk for much longer. But so here's the outline. I will first just extend the introduction that Jeremy started, and then I will give you the 3 examples, and I will let Jeremy complete the sandwich at the end with the last section. So to be more explicit about the content of Jeremy's introduction, we have 2 levels of theories. One is we call TB, which stands for bottom or basic theory. And the TT is the tainted or top theory. And tainted is just originally, I believe it was Jeremy that came up with this nomenclature, or this mnemonic device. And tainted just means that it's something like, I think at the time, I believe like thermodynamics, that is not as precise as the cleaner statistical mechanics. And this is just one example, but it stands for an analogy. And we will say that TT, the top theory, is a definitional extension of the bottom theory, if and only if the bottom theory plus some judicious definitions will imply the top theory. And this has been debated in the literature, and this account of Hegelian reduction has been often rejected. as both allowing too many theories to be reduced and not enough. And the theories that we would like and know to be reduced would not be encompassed by this. So it's been rejected as both too weak and too strong. But as here at London School of Economics, who's afraid of negating reduction? And for those of you who don't know, this is a paper by Roman and friends who explains that these are we should not be so concerned with these with these criticisms, because we can impose some natural, very natural extra Hegelian conditions, which against the too weak criticism will require the definitions to play a role in the bottom theory. So, for example, to be short and conceptually unified. And against the too strong, it requires that we allow the bottom theory plus definition to imply only an analog of GT. So a closely related concept. And so here we follow basically the philosophy of Putnam, Armstrong, Lewis on this topic. And for us, only the first two of these items will be important. So first there's the concept of specifying. So we call it specify. In the top theory, troublesome concept or property of interest, and here we follow Lewis's nomenclature and call this tau, will be uniquely specified by a web of relations to other OK concepts or properties by its functional role. So Lewis calls these old terms usually, and he just says, look, these are just names that we accept in our vocabulary, and you don't need to investigate them further, that we just accept as not being problematic in any way. And of course, this is very weak, because almost any property that you can imagine will be uniquely specifiable by a web of relations. But it's not true that this weakness implies that it is very easy to find these or specify this web of relations. There's hard work to be done, and because we don't want just any arbitrary web of relations, you want that to, let's say, carve nature at the joints or be some sort of salient to the theory at hand. And yes, so the role-occupant contrast and the uniqueness in this specification leads to infer this property, that a unique realization can imply that implies that it can be compulsory, so not optional, to identify a concept at the top theory, at the tainted theory, with a concept at the bottom theory that we will call rho here for reduced. So if you have some inference that says that that tau, that concept in the top theory, is equal to a right-hand side that specifies that term to its web of relations, and then you have in a different theory or a different vocabulary the same right-hand side of that equation, the same specification of the term, but now identifying a term or a concept in the bottom theory, you can therefore infer that the two concepts are identical. And this is a reduction, a compulsory reduction. So the standard example is psychophysical identification, mainly by Lewis in all these papers, at least how we follow that study. And you start with pain, and you specify it as the inner state that is typically caused by tissue damage and typically causes distress and so on. You can have many other terms to the right-hand side of that equation if you'd like. And then this all happens in a top theory or a tainted theory. And then you can also describe this same right-hand side as C-fiber firing in bottom theory. So let's say in this case, contingent neurophysiology. So you have empirical evidence and so on to find out what this theory is and what satisfies the functional role on the right-hand side. What is the realizer? And once you've done all this work, you can now identify pain with C-fiber firing. And it is in the Lewisian type of reduction, the bridge laws that you get are mandatory. It's tau equals rho. And so folk psychology, that we call the T-top, which has some troublesome mental terms, and it could have okay behavioral terms, but as we have specified pain in item number 1, can be functionally reduced to neurophysiology, which is the bottom theory here. And as an example in physics, Maxwell concluded that light, or tau here, is an electromagnetic wave, which is rho, which is a concept in the more advanced theory of electromagnetism, or let's say just bottom theory, so that we not prejudge which came first, which is more developed. And of course here both occupy the functional role, travels at a certain speed, but it also illustrates that uniqueness can fail because something else could also travel that fast. And in fact, we know that gravitational waves do. And the third concept is that several or even many troublesome concepts in the top theory can be simultaneously defined without logical circles in terms of the okay concepts. And this was a major worry in this in the beginning of this doctrine, because there's clearly a threat of circularity if you try to be explicitly behaviorist about beliefs and desires. So the standard example is that a belief that it is raining, and in terms of being disposed to pick up an umbrella if going out, but then that needs to invoke another inner state, a desire to stay dry, and so on. And so you can't, it seems that you wouldn't be able to do everything you want to do just with the behavioral terms. But for a body of information that is quite rich and interconnected, you can simultaneously specify uniquely several items. And so the example, the very poignant example that Lewis gives is the winner of Cluedo, which you give enough information to specify simultaneously the murder, the location, and the instrument. And an example that we gave in the paper is that to uniquely specify Ian McKellen and Judi Dench as the best ever occupants of the role Macbeth and Lady Macbeth. And so then the functional roles here can be systematically extracted from the whole theory, containing both troublesome and okay terms. And then one can try to claim unique occupants. As Jeremy presaged here, we won't really enforce this simultaneous condition. We will in the work in our paper, in fact, we only ever define a single term. We don't try to do it for many at once, but it perhaps could be done. So let me now move on to the first concrete example of these ideas in the geometrodynamical context. And this is a seminal paper in general relativity, and I don't know how well it is known by the community, but it should be more widely known, I think. It's so HKT, as we'll call it from now on, or Sergio Hochman and Karel Kukash and Claudio Teitelbaum, they assume a four-dimensional Lorentzian manifold, M, but they adopt the 3+1 perspective. In fact, there is a little bit of leeway here. They can assume a four-dimensional Lorentzian or Euclidean manifold, but we'll stick with the Lorentzian for this talk. And they adopt a 3+1 perspective. So the 3+1 perspective is you consider embeddings of a three-dimensional spatial manifold as space-like hypersurfaces of M. So this is a drawing here on the right. You see the two leaves of the foliation, and they correspond. They are diffeomorphic to the same to a single spatial surface here, and a single point on the spatial surface can be mapped to a curve that will be basically the constant spatial curve, right? As you just progress along time, the constant, and you keep the spatial coordinates constant, this will form a curve. And you define quantities to relate the coordinates of the embedding with the coordinates of the manifold. And the metric here will define something that we call the lapse and the shift of any vector field V on M. So the lapse and the shift are essentially just basically they correspond to the thickness or the duration between two leaves. And the shift tells you how, with respect to the metric, how bent your constant spatial coordinates are in the space-time. Right, so. And HKT, they show that if you transcribe some quite natural requirements about how these embeddings mesh, which is encoded in what's called the deformation algebra. And if you transcribe that into a Hamiltonian framework as a constraint algebra, that will describe how the spatial geometry on sigma changes. Then the Hamiltonian must be the usual Hamiltonian in general relativity in its ADM form. So let me say a little bit more about this. The idea is that you have these surfaces and you have vector fields that you can imagine as changing the foliation. Any diffeomorphism would change the foliations. You can see that, and diffeomorphisms are generated by vector fields. So infinitesimally, you can think of these vector fields as pushing the foliation this way or stretching it in that direction and so on. And then you can think of what happens when you compose these types of diffeomorphisms in one way and then the other. So for instance, if I do it in one direction and then another and the opposite way, I'll get a certain what's called a hypersurface deformation algebra. It's what is the end surface, the surface that I end up with after this process. And then on the geometrodynamical side, you can also think of a Hamiltonian as pushing the fields forward, not the leaves, not the spatial manifolds, but not the manifolds themselves, but the fields that are defined spatially, the spatial fields on these surfaces, and how the Hamiltonians push them forward in time and so on. And you can require that these Hamiltonians, the action of these Hamiltonians, successive actions, when you use the Hamiltonian to push it forward or to just shift the fields around in the same hypersurface, how they will commute, their commutation properties. And you can require that the dynamical side of this, so this geometrodynamical part, reproduces the idea of the hypersurfaces in space-time. And I think at the time surprising, but a very elegant result is that you get the unique occupant of this role, the unique Hamiltonian that satisfies these commutation properties is the ADM Hamiltonian. So in Lewis's notation, we would say that the generator of how spatial geometry changes over time that reproduces the deformation algebra of hypersurfaces, yet tau, is the ADM Hamiltonian, that is rho. Sorry, any questions? Because I'm going to skip the details. We can talk about it later, or I can answer specific questions later. But if anyone has a question or doesn't understand something now, you can definitely stop me and ask.
Can I ask one question?
Yes, of course, Karim.
So do we not need the on-shell requirement as well?
Yes, yeah. So in fact, you don't need. It's a little bit okay. Let me. You don't need to impose the on-shell requirement itself by itself. So what happens is the following: is that the requirement that the requirement that it meshes in the right way. What they ask for is that if you do two of these deformations, you will end up in the same solution of the equations of motion. So let's say I do one deformation like this, and I do another deformation of this, and I want them both to be to essentially, or let's say the difference between the two to also be a solution of the equations of motion. So they translated this in many different ways, but they ask essentially that it doesn't matter physically which which deformation you put first. So physically, they say, let's say I have one vector field, let's call it X, and I have another vector field in spacetime, let's call it Y. And in spacetime, there's no question of what happens, but when because you always end up in the same spacetime if you deform these things. But now they're asking, if you push the fields forward using a the corresponding Hamiltonian generator of X and the corresponding Hamiltonian generator of Y, if you use the HX and then HY, do you get the same space-time or the same solution, let's say, if you do the opposite direction? They say it's the same geometry, essentially. And this, at this level, if you just impose that, you require that the Hamiltonian evolution generator is in fact a constraint. And then that requires that this only works on shell. So there's this kind of bootstrapping of the on-shell requirement.
So maybe this is probably a longer thing, which maybe we should do separately. But so you're saying you don't need to know the Einstein spacetimes. You can just use the isometry classes of the spacetime you're building.
Yeah. So you definitely don't start with something that satisfies the Einstein equation.
Because of course that's going to be problematic for your argument if you did, right?
Yes. Yeah, you don't start with that. You derive that it is a constraint.
Maybe let's leave this for another time.
Yeah, I want to say, let me come back to that in question period, maybe.
Okay. So I am not going to talk about the details of that. Now let's move on to Schuler, Duhl, and Giesel. To be honest, this is it's a more recent and I believe less well understood work. It uses a very algebraic language. It's not that easy to understand what is going on behind the hood, but let me try to translate our understanding. The first stage here is the functional reduction of a generalized chrono-geometry to a dynamics of matter and radiation. So for them, a four-dimensional manifold, but in principle, no Lorentzian metric is assumed. And then you try to extract a functional role of duration by assuming that the dynamics of these matter fields, whatever it is, will be deducible or is deducible from a diffeomorphism invariant action functional and will obey some certain requirements about being well-behaved and predictive, which are translated into algebraic requirements on properties of its equations of motion. So perhaps here it is good. It might be good for me to illustrate what they had in mind. And as Jeremy said, Schuler is the main guy here, and he had this theory about the basic variables of gravity not being a metric, but something that or basic variable of geometry, let's say, not being vectors, but as being areas, so directed area elements, and think of evolution of these directed area elements. So it's a very different conception of geometry that he's trying to implement here, and in Geometrodynamics in principle. So he was searching for a more comprehensive notion of space-time. And so what he implemented are these weak requirements about being well-behaved and predictive. And in the second stage, SDG, which stands for Schuler, Duhl, and Giesel, will adopt 3+1 perspective and study the evolution of 3 geometry coupled to the first stage's dynamics. So just to be clear, what they do in the first stage is they look at the equations of motion, and then they're able to define things like what is in the light cone and what is spatial, what is, let's say, not in the light cone, but also defines a surface. And then you can ask what kind of structures are pulled back to the surface. And you can define a kind of induced geometry on these surfaces. And then you ask that, and then you find that they must be consistently propagated. And then they try to implement the HKT argument to find what would be the consistent dynamics for this emergent space-time. And using the HKT Hamilton technology is the best way to do this. So for just the theory of electromagnetism, so just beginning with the equations of motion for electromagnetism and nothing more, not knowing that it comes from a space-time Minkowski metric and so on, they are able to bootstrap this entire algorithm and show that in fact it is the ADM Hamiltonian that is consistent with this. So in their case, the functional reduction would read as follows: the ADM Hamiltonian is the concept that uniquely satisfies, and then open quotes, describes how spatial geometry, as determined by the assumptions 1 and 2 for electromagnetism, changes over time. Or in Lewis's terms, it would be ADM Hamiltonian is the unique, or rho as the reduced, is the unique occupant of the role, describes how geometry, as determined by 1 and 2 for electromagnetism, changes over time. And again, we get the same idea that rho is tau. So Roman, how much time do I have, just so that I can pace myself?
So you have another 15 minutes.
Okay. Okay, good. I think that's so. As Schuller and friends stress, this work would enable a systematic exploration of alternative gravity theories, those concordant with 1 and 2. So what they mean by this is that you could just give me any equation of motion that satisfies these algebraic properties that are translated into being predictive of the future and so on, and they could turn the crank and give you what kind of spacetimes, notions of spacetime, or geometries of spacetime, or notions of geometry would be compatible with these dynamics. So in this sense, it would be the reduction of general relativity is only a local reduction, because there could be other things if you put in different matter fields. But it is very difficult to do. So there are no explicit examples of other matter dynamics, different types of fields with different types of dynamics, for which they're able to completely complete this algorithm. So, and of course, I mean, to the Oxford, to our neighbors here, people, philosophers of physics, they would recognize in this approach some echo of the dynamical approach to space-time theories of Harvey Brown. And yeah, and I think that's warranted. They do remind us that we need to understand constructively how matter manifests geometry. And for me, this is one of the most explicit attempts at doing that. It's well, mathematically, it's quite precise, although at some points a bit opaque. Okay, so again, I'm going to skip all details. And finally, my paper with Vasudev Shyam, who I forgot to invite to listen to this talk, but anyways, it's recorded, so I can show it to him later. We did not assume ab initio a space-time manifold and no diffeomorphism invariant action functional. Let me just say that Vasu and I were motivated by slightly different objectives. I was thinking of shape dynamics, and Jeremy will tell you a little bit more about shape dynamics in the last 5 to 8 minutes, if I can finish quickly enough. And Vasudev was motivated by holographic theories at infinity that also exist in less space-time dimensions. But so we only assume that the spatial geometry of a 3-manifold is to vary over time with at most second-order dependence on momenta. This will become a little bit clearer in what follows. So I'll tell you a little bit more about this. about that. And that the spatial geometry of the three manifold is to vary in a manner that is locally definable. And then this is in fact enough to construct a space-time with a Lorentzian metric and to show that the geometry evolves over time according to the general relativistic Hamiltonian or ADM Hamiltonian. So maybe I should say a few more words. This is still a little bit cryptic. What we did was to think, just given let's say how Jeremy and I envisaged the top theory here. The top theory here can be something rather crude because we can dump all the complexities into the bottom theory. So the top theory here we can think of as a theory of duration that that relates to time, to these Machian ideals of time as the measure of change, and we require duration to be determined or specifiable locally, let's say at disjoint regions, and once you do that, we have this meshing criterion that says that if you define duration in different places differently, and you again concatenate as Hodgman, Kukash, and Teitelbaum do, different notions of duration, the order by which you choose these different notions won't matter to the final geometrodynamical state. Or you don't need to bring in geometrodynamical state. You can just talk about general state or physics. And then when you transcribe that into the Hamiltonian framework, you must require that the Hamiltonian is only second order momenta, because we were only able to show uniqueness up to second order momenta, not that it fails for higher order in momenta. But you're able to show that the ADM Hamiltonian rho here is the unique one that is the generator at most second order momenta of how spatial geometry is over time in a locally definable way, meaning that it meshes in the right way without assuming space-time. And again, writing this role as tau, we have rho is tau. And I think with that, I can, well, maybe I should, since I have a couple minutes, maybe I should give you a little bit more detail here. I won't tell you what the assumed form of the Hamiltonian is. It's a bit complicated. But that maybe this requirement that evolutions mesh in the right way is useful. So in the top theory, all we require is that delta here is some difference in this let's say this quantity phi. In 1 and 2 means that there's some evolution along one notion, or we would say in the Hamiltonian framework 1 lapse, and then an evolution according to another lapse, 2, or 2 different notions of duration for this process on the field phi would physically equal the same quantity phi undergoing the opposite order of these 2 evolutions. So this is the requirement here, and for them to be physically equal in the Hamiltonian framework means that in our jargon, because once you assume a spatial ontology, and you can think of the diffeomorphisms, the generator of spatial diffeomorphisms as being gauge or symmetry. Again, this is bootstrapped as in the Hodgman, Kukash, Teitelbaum framework, but you didn't need to do that way. Then that means that for these 2 to be physically equivalent, the difference between them has to be gauge, has to be a generator of gauge, and this is this Poisson bracket between the quantity phi and the spatial diffeomorphism generator. And F here doesn't really matter what it is. And this is the technical requirement that Vasudev and I imposed, essentially. And once you translate what these delta 1, 2 are to the geometrodynamical context, you can turn a crank, a very complicated and enormous crank, but you can turn the crank and find that the only ones that satisfy the conditions that we impose up to second order momenta are the Hamiltonian ADM, which is, I didn't show it because it's not entirely relevant, but we can go back to it in question time. And I think now I pass it on to Jeremy again.
Okay, dear Henrique, thank you. I turned off I turned on my, can everybody hear me okay? I've turned on my microphone again. In this last section, I know there's a danger of overrunning time, especially with me talking. So let me just emphasize there are 2 points. There's a philosophy point and a physics point. And then there's a short conclusion with a diagram of what's happened in the paper. The philosophy point is on this slide. Just zooming out from all the technicalia, there is, many people will recognize this famous quote or quip from Russell in the Introduction to Mathematical Philosophy, where he is being rude to other philosophers who, instead of deducing some doctrine that has merited kind of philosophical scrutiny and you're trying to reconstruct it exactly or vindicate it or legitimate it, instead of just postulating it in some crisp, clean and preferred version, Russell says you must deduce it, right? And he says the opposite is theft, whereas I, Russell, by deduction, undertake honest toil. And that famous quip is, say we, unfair, because up in the top theory, with its troublesome or problematic aspects, in particular those troublesome terms that you want to fix the interpretation of and give a functional definition for, up in the top theory, never mind the bottom theory and never mind the enterprise of reduction, it can be hard work and therefore honest toil to write down a clean version or and we mentioned this with the names of Dedekind and Malamud in an early slide when we first talked about functional definition. So in particular, imagine a Euclid through to a Hilbert trying to axiomatize geometry. You've got a preferred collection of concepts, point, line, between, congruent. You're not trying to give some extra theory of what a point or a line is. Nevertheless, it can be hard work and honest toil to write down an axiom set that delivers all that you wish to say with those concepts or words. Similarly, the HKT deformation algebra or the generalized geometries of SDG, all that's upstairs in top theory, right? In any case, the physics point is that there is a rival or cousin theory to general relativity, shape dynamics, which this talk, though not the printed paper, is silent about. Henrique is one of its inventors, and I will not pretend to understand it, let alone report it. But it's true that as it was conceived some 10 years, 8 years ago, it is a 3+1 theory. It emphasizes shape rather than length in ways I won't try to explain, but it postulates the ADM Hamiltonian that we've been discussing. And in its scheme or framework, there are other Hamiltonians that look more natural. And therefore, you might say, shape dynamics has just lent on the previous success of general relativity to give empirically adequate as well as kind of theoretically amazingly interesting conception of spatial geometry changing over time? And isn't that a sort of naughtiness of some kind? One might even say postulation, one might even say theft. Well, this GS result, the third project discussed, shows that that's just a happenstance of history, right? An advocate of shape dynamics can actually transcribe the Gomes-Cheyenne result into the scheme of shape dynamics and vindicate the postulate, or indeed not just vindicate, but deduce the ADM Hamiltonian from constraints of the type that the GS theorem gives one. So let me leave it there and proceed to conclusion. Dear Henrique got this excellent table. On the first two columns are assumptions. So there we see 4 projects. For example, Gomes doesn't postulate a 4-dimensional manifold, but HKT and SDG do. Shape dynamics does not. As we've said, HKT actually postulate a Lorentzian metric. SDG do not. Do we recover the orthodox ADM Hamiltonian? Well, yes, in 3 or 4 cases. The question mark for SDG is simply to signal that their achievement so far is limited to familiar matter like classical electromagnetism. And in what sense is there a uniqueness result? Meaning as in the functionalist mode? Yes, again, there's a uniqueness theorem in 3 out of 4. So if I could go to the last slide, Henrique, the take-home messages are, well, space-time functionalism is, of course, an ism, and it comes in various versions. And we've been apologetically, but manifestly silent about important versions that are in the literature. By Eleanor Knox, who proposed the phrase, and especially looking into the usefulness of the notion in the context of quantum gravity, Lamb and Wuthrich and Huggett and Wuthrich. So what have we done? Well, what we wanted to urge is that 3 endeavors in foundations of space-time theory, especially deductions of the ADM Hamiltonian, do illustrate a certain kind of specific kind of functionalism, namely functionalist reduction, and that this bears on things like dynamical approach. So thank you very much, and we invite discussion.